Hello, everyone. My name's Adam Wexler, and I'm a third-year doctoral candidate through Wageningen University and TU Graz in Austria. But I'm originally from the United States, and I work and live up in Leeuwarden now. And I get questions often, why did you move from the United States to the Netherlands? And the answer is simple: water. We've heard that several times today, that water knowledge is the major export from the Netherlands. And I think that when we think about water, we all have different understandings of it. Sabina has a very different understanding of water than any of us in this room do. And I'm a research scientist, so I don't do water management per se. I ask the question, what is water? And where can we find it? And if we look, we find that water is everywhere. This is a recent image of the universe. Each of those dots is a galaxy. There's about 43,000 of them there. And throughout that entire volume, we now know there's water. There's water connecting the space between galaxies. There's water surrounding nearly every star. And there are more and more planets that we're finding that likely contain water, like our own. Water is essential in the process of the birth and death of stars. This is an image recently generated from data gathered through research done at Leiden University, where they found that during the formation of a star, much like our own sun, water is ejected from the star, and it's ejected at speeds 200,000 kilometers a second. And it's ejected in such volumes that it dwarfs the amount of water that we have on our planet. So during the formation of our solar system, our star was creating the water that we now have in our oceans and in our bodies. Water is also ejected in giant, massive charged jets from the centers of galaxies. These water masers, as they are known, send out radio signals into the universe. So there's energy being radiated, and it's being radiated by water. It's being driven by the forces of gravity, by the forces of nuclear fusion, and by forces that we have yet to understand. And it's the reason why we have this very special place in the universe, where we can be here right now, experiencing this thing that we call being human. The water that's on this planet came from our star. It came from the stars before, because this place in space has seen the death and birth of many other solar systems. But the water on this planet is something that we don't understand, because water is unusual. If you ask somebody in the physical sciences what they know about water, almost all of them will say, well, it's pretty weird stuff. Depending on who you ask, you'll get between 69 and over 100 anomalous properties. Water is very good at dissolving everything it comes in contact with. This is great. It gives us beautiful things like the Grand Canyon. It helps to shape the landscape. It helps to bring nutrients from faraway places to make for fertile land. Water also has some secrets that we may not necessarily know. And this is the only graph I'm going to show you. Yes, it's the only graph I'm going to show you. And what this is it's an absorption curve. This is the absorption curve for water. And it goes all the way from the ultraviolet out into the radio wave. And what I want you to look at is this valley right here. This spot is how we see water. This is the only place in water's absorption spectrum where it doesn't absorb light, meaning we think and we experience that water is transparent. And what does this mean? It means that when water sees light in the visible spectrum, it doesn't interact with it. It lets the light pass through. But in the ultraviolet, in the X-ray, in the infrared, in the radio wave, it interacts with it. This is why we can heat up our meal in the microwave. We send some radio waves in the gigahertz range, and we heat up the water molecules. We cause them to move. This is important. Water has another anomaly. It's a strange one, and it's perhaps one of the most important ones for survival on our planet, and that's that when it undergoes a phase change from the liquid state to the solid state, it loses density, and so ice floats. And this is key because without it, all the fish in the sea would die. Other things can float on water. Here's a 1 yen coin made of aluminum floating on a glass of ordinary drinking water. The very high surface tension of water is an anomalous property. And water has the ability to hold a lot of heat. Water has one of the highest specific heat capacities for a liquid of its kind. And this is very important for things like weather, indeed. And this is Hurricane Katrina. This was one of the top 5 most deadly hurricanes in US history. And when Hurricane Katrina came ashore, when it crossed over the shoreline and began to inundate the city of New Orleans, it took 5 hours. And it dissipated 54 trillion watts of power during that period. Just to put it into perspective, if we break it down on the hourly basis, that's 83% of the total electrical energy consumption in Europe. So this one storm transferred a huge amount of energy, and it did it through the transfer of water. Now, water is essential. And why did I come to study water to begin with? Because there's so many things that we can study in life. And actually, before I came to do science, I was working as a massage therapist. And, you know, it's a great profession. I was always happy at the end of the day. But I really started to wonder, why do people get better? And I started to dig into the literature. When people come in and they're not feeling well, and we do some work on them, and then they get better. Bodies heal. And why is that? What's happening? What makes something alive? And I started to think about it, and I realized, well, water is a key ingredient in life. Why is that? And if we go back to those anomalous substances, the anomalous properties that I mentioned, they're often ascribed to something called hydrogen bonding. And it's these properties that make water able to support life. It's these properties of high specific heat capacity, of high surface tension, the density anomalies, the ability to dissolve many, many different substances and interact with many, many different substances that allows life to arise in the oceans, that allows life to occur in our bodies. Water shapes our landscape. As we've already seen, it carries and transports many things. The patterns that it makes, we find them in our biology, we find them in our landscape. This is a slice through a mammalian cerebellum. We have these in our own brains. They're responsible for our balance. And they inspire us. Human beings, we're made of mostly water. In each and every one of us, there's something around the order of 10 to the 27 water molecules. And all of those water molecules are in intimate contact with each other. But water has some surprises for us. And back in 1893, there was a researcher who was working on steam boilers. And he had been discussing with some of the boiler engineers about a problem that they were having. They were receiving electrical shocks. And he was curious, how is it that a boiler is creating electricity on its own? And what he realized was that steam flowing out of a leak would charge up this particular spot, and these guys would get a little zap. So he built himself a research boiler, and for some unknown reason, probably after drinking a bit of wine, because he used 2 wine glasses, he hooked up his steam generator to 2 vessels containing pure water. And when we zoom in and turn on the current, we'll see something interesting. At first, we see the surface begin to respond. The lines will get a little bit closer together as we add a few thousand volts. And then snap. You really can't see it in this picture, but here we'll take another look. The water forms a connection. It leaps out from one container, leaps out from another container, and like two hands reaching across the space, it makes a watery connection. Now those were Teflon beakers, we can do it in glass. Now this phenomenon was discovered in 1893. And it sat that way as just sort of some weird party trick until about 2006, when my promoter and my supervisor one day saw this video on YouTube because it's something that people thought was interesting but nobody understood. And they repeated the experiment. And when they did that, they started to wonder, well, there seems like there's a lot of dynamics happening here. It oscillates. Sometimes it forms, sometimes it doesn't. How long can we stretch this thing? Well, we've gotten to 3 centimeters. So about 30,000 volts and 6 milliamps, you can get to 3 centimeters with this thing. And the behavior of a long bridge is very different than the behavior of a short bridge. But I want to impress upon you that this is not a weak structure. If I take a glass rod, for example, I can pass it through the bridge and the bridge won't break. I can make it vibrate like a guitar string. And when we look at it, and we look through it, and this is a high-speed video, so we're looking now at about 1/1000th of real time. We see these distortions. We see movement happening through the bridge. And these are density anomalies. So that was one of the first clues. We said, well, that doesn't make sense. Maybe it's just thermal in nature. But we see both convergent and divergent structures, meaning that we see high-density regions and low-density regions. When we look in the infrared, we do indeed see that there is an oscillatory pattern where it becomes very hot in some region, and then that region moves across, and then maybe moves back again. And actually, we've been watching these videos for quite a while, and then some researchers at NASA asked us, well, have you guys ever done spectroscopy on this? Have you looked to see if the infrared light that's coming out of this is just thermal? Because everything heats up in the universe and gives off black body radiation. Well, what we found is that this radiation is non-thermal. Part of it is thermal, but there's another peak within the thermal spectrum, and that has something to do with molecular dynamics. Because we've got all these water molecules, and they're in this bridge, but the electric field is changing the way that they behave. So then we had to come back to a very fundamental question. What's driving these dynamics? Is it simply the response of the liquid to the electric field? Or is there something else happening? And this was important because in terms of science, in terms of the scientific community, there was a big debate about this water bridge phenomenon. Is it just simply electrohydrodynamics? Do we already understand everything that's there? Or is there something we're missing? And ultimately, it gets us to this one question. What is water? Now, most of you might be thinking right now, well, that's easy, it's H2O. Chemically speaking, on average, if you wait a long time and don't really care too much about differences that may occur between one region and another, yeah, H2O is a very good descriptor. And it's an easy descriptor. And a lot of people are using it to try and understand what's happening within liquid water. And this is a molecular dynamics video that was produced by researchers at the Free University of Berlin, and it always pauses here for a moment. The green lines were hydrogen bonds. And so here we see now just two water molecules bonded together through an interaction known as hydrogen bonding. And I'll talk a little bit about that in a second. But you see here this graph. This graph is a plot of their relationship. So at first, they're very close to each other, right? They're like sweethearts. They're holding hands. There's something binding them. And then something happens. A fluctuation occurs. And they move further apart. They attempt to regrasp each other, but they eventually lose the connection. This happens on the order of picoseconds, which is, means for us that in every second there's a lot of changes, about 10 to the 12 changes in every second. So we knew this about molecular dynamics, and we knew that there was something strange in the emission spectra of the water bridge. And so we went to some researchers here in Amsterdam who have an ultra-fast laser. And ultra-fast lasers are really cool. They make light that is at about 10 to the minus 15th of a second. So if you chop up a second into 1 with 15 zeros behind it, you get one of these light pulses. And with that, we can look at those dynamics. So the dynamics that we saw in the simulation, you can actually measure in real systems. And what we found was that the relaxation time, so this time that tells us something about how the water molecules are connected to each other, changed. In liquid water, it takes about 740 femtoseconds for one of those OH bonds to relax. In ice, it's down around 400 femtoseconds. In the water bridge, it's about 620, 630 femtoseconds. That's interesting, because when we go from ice to liquid, we have to cross through what's known as no man's land, which is that phase transition place. It's a jump discontinuity. You're either ice or you're liquid water. Until we had done the work on the water bridge, no one had ever seen a time in that no man's land. So all we did was add some electrical field strength. Put some electrical field onto some water, and now we've moved liquid water closer to being like ice, or have we moved ice closer to being more like liquid water? Well, there was a problem with this data. And it's something that I'm not going to show you as a plot, because frankly, it's something that I'm still struggling with, because it's a paradox. This plot tells us that water molecules in the water bridge are more tightly bound to each other than they are in normal liquid water. But what we also found is that the amount of time it takes for that energy absorbed by the system to re-radiate through the system is longer. So in other words, it's as if this group of people here and that group of people over there have a very close relationship, but there's not much communication between the two. And this landed us into some hot water, because it revived a debate and it plunged us into an ongoing debate about what is water. Is it one liquid or is it two liquids? And this goes back to the time of Röntgen. Röntgen is the father of X-rays. He was one of the first people to make X-rays and to bring this technology to us, which we use a lot in our materials from X-ray imaging. When we do X-ray work on water, there's a problem, because we wonder if it's one or two liquids. And what we need to do is we need to go beyond thinking in terms of black and white. What we've essentially found is that by adding an electric field to water, we can change its properties. And we can change its properties in a way that go in both directions. On one hand, it makes things more tightly coupled. On the other hand, it makes things more loosely coupled. So it's probable that we're heading towards a liquid-liquid phase transition. But there's as yet no solid proof for that. Well, are there other things that we know about in the universe that have this dual ambiguous nature? And indeed there are. Photons are one of them. Or are they light waves? Or wait, are they photons? This is one of the fundamental questions that gave rise to quantum mechanics. It gave rise to quantum electrodynamics, gave rise to quantum field theory, which is now very popular because we intuitively interact with this concept, that there is something connecting us, but that we are individuals and we are discrete. So looking at the lessons that we can gather from quantum mechanics, from photon dynamics, and learning a bit from ourselves. This is a map of the internet made in 2011. We can see that there's a lot of interconnectivity. And those hydrogen bonds that predominate liquid water, that predominate and give rise to the anomalous properties that water exhibits, it's a network. It's a network very similar to our own internet. And if we combine those two concepts together, and then we take a look at ourselves, and the reason why I'm coming back to people right now is because the electric fields that we apply to water to make a water bridge are of an order of magnitude or two less than the electric fields that exist within every one of our cells. The water in our bodies may very much be more like the water in a water bridge than it is the water in a drinking glass. So there are things that we need to do to understand water, and there are things that we can do to understand ourselves. And I think that by combining those two efforts, we're going to find a new understanding of our place in the universe, and ultimately we will find a new way to deal with our resource that is water and our resource that is human being. So I thank you for your attention and have a good evening.